self-induction. Now, self-induction is the phenomenon, of producing EMF to oppose the change in current in a coil. That means, let me explain. Suppose we have a coil here. Suppose this is a coil, and the current is carried by this coil. The current is carried by this coil, and if there is current, then there will be definitely magnetic field linked with this coil. And if you change this current, if this current is changed, then there will be change in magnetic flux. There will be change in magnetic flux, and due to this change in current, there will be change in magnetic flux, and due to this change in magnetic flux, an EMF will be induced. This EMF will oppose this change in current. That means direction of this EMF will be opposite to direction of this current. So this process is self-induction. So hope you have understood this. So we can write the definition of self-induction this way. That so it is the phenomenon of inducing EMF in a coil to oppose the change in current in itself, current in the coil. So this is the definition of self-induction. So here you see, as this current changes, magnetic flux linked with the coil changes. So that's why we can see this phi magnetic flux is directly proportional to I, right? If it is directly proportional to I, then we can write that phi is equal to, there should be a constant, that is L, and I. This is constant of proportionality, and this is called coefficient of self-inductance, or simply you can say self-inductance. Self-inductance. This is coefficient of self-inductance, or you can simply say self-inductance, right? Now you see, what if the current in the coil, suppose 1 ampere current, 1 ampere current, then what will happen? Then phi will be equal to L. If this current I is equal to 1 ampere, then this self-inductance will be equal to phi. That means we can define this self-inductance. Therefore, this self-inductance can be defined as self-inductance can be defined as the magnetic flux linked with a coil when the current in the coil is 1 ampere. So that's how you can define self-inductance, right? Because you can see when here we have got that phi is equal to L into I. When this I, that means current in the coil, is 1 ampere, then this phi will be equal to L. Okay. Now the induced EMF in the coil, Faraday's second law gives that EMF induced in the coil is minus phi by T. And here you see this is nothing but this L is constant of proportionality, which is self-inductance. So it is constant. So when you put phi is equal to Li here, d by dt of Li, then this L can be taken out as it is a constant. This L can be taken out as it is a constant. So hope you have understood this. So that's a minus L di by dt. We can. So this is the induced EMF, right? So hope you have understood what is self-induction and what is self-inductance. And this self-inductance and self-induction, it depends on three. This L, self-inductance, this L depends on three factors, and those are what? Number of turns in the coil. So how many turns are there in the coil? Number of turns in the coil. In the coil. And it also depends on the cross section. This cross section of the coil. And also depend on the nature of the core. So what is the core inside the coil? It may be air, it may be other material. It depends on that. Nature of the core material. Core material. These are the three factors where on which this L depends. So hope you have understood this. Now let us discuss about self-induction in a solenoid. Self-inductance in a solenoid. Right? SI unit of self-inductance is Henry. Remember that SI unit is Henry. Okay, of self-inductance. Remember that. Suppose we have a solenoid. This is a solenoid. This way. Let me draw it properly. Right, and this is the current, electric current, and that's why there will be definitely magnetic field and so magnetic flux, right? Now let me consider this core of this solenoid. That means its interior part is suppose air. Okay, the interior part is suppose air. And its cross-sectional area, this cross-sectional area, suppose A be its cross-section, and this length is suppose L, total length is suppose L, and let us consider it has n number of turns. Let us consider just n number of turns. Total number of turns is n is equal to number of turns. Right. And let us consider that small n is equal to number of turns per unit length. So if in L length number of turns is n, then in unit length it will be n by L. So number of turns per unit length, right? Let us consider that. So A is the area of cross section. So then in that case, this magnetic field set up here due to the conduction of current will be given by B is equal to mu naught n I, right? Mu naught n I. So where mu naught is nothing but mu naught is the magnetic permeability of free space. Right? That means as we are not putting any material, we have considered air, so we are writing here mu naught. So let me tell you what is magnetic permeability. So suppose this is a material, and magnetic permeability of the material is the ability to permit the passage of magnetic field lines of force through it. That is what magnetic permeability. Okay, so hope you have understood this. Now here you see this n, this is what number of turns per unit length. So let me write B is equal to mu naught n by L into R. So you can write that way, right? So now you see magnetic flux phi is B dot A, B vector dot A vector, right? A vector is the area vector, B is the magnetic field, right? B is the magnetic field. As there are n number of turns, so we have to put here n. Okay, so hope you have understood. And dot product of these two is what? BA cos theta. BA cos theta. So here you see theta is the angle between B and area vector A, magnetic field and area vector A. Now here you see. So this is the area of cross section. Here is the area of cross section. This is. So this is the direction of magnetic field, and in the same direction we have the area vector. Right? So angle will be 0. That means, so imagine this. This is the face of the cross section. This is the cross section of this solenoid. So facing this in that direction, and magnetic flux, direction of magnetic flux also in that direction of magnetic field also in that direction. And if this cross section is facing towards right from your point of view, then in the same direction the magnetic field lines are passing going in the same direction, then we can say the angle between area vector and the magnetic field is 0 degree. So that is theta equal to 0 degree, and cos 0 degree is equal to 1. That's why we can write phi is equal to NBA into 1, that is NBA. Okay, so hope you have understood this. Now replace this B by this value here, by this value. So B is equal to what? Phi is equal to n mu naught n I by L into A. So here instead of B we have put this value, right? This is I, right? So which gives n square, right? That's gonna be equal to, let me use proving, that's gonna be equal to phi is equal to mu naught n square I A by L. So this is magnetic flux, right? Then we also know that we have already derived this, we have already got this relation that phi is equal to L, that is self-inductance, into I, correct, right? Now from this relation, from these two relations, from this is 1, this is suppose 2, and we know this, isn't it? We know these things, right? And from 1 and 2, from 1 and 2, what we will get from these two, you will get Li is equal to mu naught n square I A by L, right? So here this I cancels this I, and then our L will be this capital L, self-inductance, is equal to mu naught n square A by small l. So this is the expression for self-inductance of a solenoid. Self-inductance of a solenoid. This is the expression, right? Just wait. Let me write on that side. Let me clean this. So from this state, what we have got here, L is equal to mu naught n square A by L. This is self-inductance of a solenoid. Self-inductance of a solenoid, right? And instead of air, suppose we have put here a particular material and it will have a permeability, so that is suppose mu, okay, for a core material of magnetic permeability, which material of magnetic permeability, mu, magnetic permeability mu, this L will be is equal to, instead of mu naught we will write mu. Now you see, instead of air, if we put a material here of magnetic permeability mu, suppose, so let me clean this part, okay, if you have written. So self-inductance of a solenoid, if the core material of the solenoid, or you can say if the core of you can say that if the core of the solenoid is a material of permeability, magnetic permeability, mu, then its self inductance is given by L is equal to, instead of mu naught, now we will write mu n square cross section A by L. So this is the formula. If the core is of any material with magnetic permeability mu, right? So this is about self-inductance in a solid. So hope you have understood this.